So how do we do, at the moment, how do we show people what an explosion can do? Well, there's basically three ways. Modeling, which requires us to actually predict or design the explosive device, the amount of explosives, the type of explosive, the way it's packaged, where it's going to be placed, how it's going to be triggered, take details of all the surrounding area, and then model them using different levels of computing power, from some fundamental calculations on pressure over distance through to highly sophisticated computational fluid dynamics and finite element analysis. But that all takes time, takes a lot of detailed knowledge of what we think is going to happen, and it can't be done quickly on the day. It's the sort of thing you do when you get back to your desk. Another way we have of indicating the amount of damage is by using blast safety tables, but hopefully based on some rational calculations. We know that a bomb of a certain size will have this much blast danger, this much fragmentation danger radius. We then add a safety margin, add grandmother's age, double it all, and then push it out even further just to be safe. And some of you have heard me speak before about some of the guidance come out from government agencies where there's an 800-metre evacuation distance for a 500-gram pipe bomb. And there is absolutely no basis in fact on any of that. So safety tables are good for providing safe distances, but they're no use at all if you're trying to figure out what will happen if a bomb explodes. And the third, and probably most common, is rule of thumb, based either on experience or best wishes. If we stand here, we'll be safe. This wall should survive. Oh, the whole building will collapse. Yeah. Sometimes they can be quite accurate if the person's experienced and has some technical knowledge, but very hard to justify. Blast is complex. Blast comes because we have an explosive, usually a solid, which we convert to a gas. And it happens in milliseconds. And of course, a gas takes up a lot more room than the solid, and so therefore it wants to expand. And it starts expanding at supersonic speeds, eventually dropping down to the speed of sound, which is around about 700 kilometers per hour, and you can't outrun that. And it is that traveling wall of compressed air traveling at the amazing speeds that does the damage, shatters buildings, throws furniture, and injures people. Although it's a gas, it reacts basically we study it with hydrodynamics, as if it was water, the way it flows around and over and presses up against things. So we talk about gas dynamics and hydrodynamics when we're trying to study it. And it is a complex area of science. As a couple of examples, this is a diagram of what happens if 5 kilograms of TNT was to explode. The red area is lethal, but it's only a couple of meters. The blue, the edge of the blue on that hemisphere that's shown there, that arc, is the limit for ear damage threshold. So, or the threshold for ear damage. So if you're closer than that, there will be damage to the body, starting with the eardrums, which are the most frangible, but other soft tissue damage, lung damage, and the closer you get to the seat of the explosion, the greater the pressure and the more injury occurs. This is a video that shows how blast flows. Let's see if I can get this to run. Oh, there we go. Shows how blast flows around corners, through gaps, builds up in corners and areas and reflects back on itself. It's a great model using some very sophisticated software, and it's there purely to show the flow of blast. What it also represents is that the walls are of infinite strength. Now, that is not how it would really occur in a real building, but that's not the intent of that demonstration. What we end up with after doing a blast analysis is something like this, which is a blast contour diagram. For a certain amount of explosive at a certain distance, we can calculate how much pressure is applied to the building in different areas. And obviously some areas receive a lot of pressure and are likely to fail structurally, others less so. But again, it's not the sort of thing we do on the day. We gather the data, take it back and write it up afterwards. This one is the Edward P. Murrah building in Oklahoma City. And the reason I put it up is to show just how far the damage will go. The red dots represent broken glass, and that can be a result of the blast being funneled down what's canyons, as they're known, reflecting around corners, and obviously it's related to the type and nature of the glass and the framing for that glass. So quite a large bomb, but a huge amount of damage over a big distance. So how do we show it in real time in the real world? Again, the paper that was presented to Parari 2019 listed a set of requirements that was desired for anything that was trying to replicate blast in any way. And this is they, and they're reasonably straightforward. We wanted it to be scaled in the way that blast is. Blast, because it's hydrodynamics, fades very quickly, fades on a cube root wall. Radio frequency, for example, sound waves, they tend to fade on a square root wall. So blast dissipates very quickly over distance. And I won't go through all of them, but it needs to be reflected by strong walls and to penetrate thin walls to give us some indication similar to blast. Ideally, it should flow over buildings the way that gas does in its hydrodynamic form. It needs to operate out to a distance, and we chose the equivalent of 100 kilograms of TNT as an aiming mark. And of course, whatever was designed had to be safe to use, transport, be able to be moved across jurisdictions, and ideally relatively cheap to purchase and operate. It was some 25 years ago that the concept of using radio frequency to indicate blast effects was first raised over a coffee. And there are some real similarities. If you choose the right frequency, it will reflect off solid walls and penetrate thin ones. It will reflect around corners. If you're clever enough with the software and have the skills and the technologies there, you can scale it to get similar indication of effects over distance. Initially, it was a great concept, but there was no way it could be done. A few years ago, we had a look at it. And again, the technology wasn't really there to achieve what we wanted. But it was resurrected just a couple of years ago by a company called Layer 3 Services. And we found that two things had happened. The computing power had increased, so we were able to do a lot more in a lot smaller area as far as some clever algorithms went. And the other thing that had really come up was Wi-Fi. And we used the Wi-Fi frequency. It's internationally accessible, it's well known, it's used anywhere, it's legal everywhere, and it happens to be one of those frequencies that will reflect off solid walls and penetrate through thin ones. So it had a lot of the things we were looking for. So a system was developed called Explosim. That's the brand name for it. It was developed by Layer 3 Services to exactly try and replicate, or in fact, the word we use is emulate, because replicate means it will do the same as. Simulate has similar meaning. Emulate means that it will reflect the type of event that we're looking at. So we talk about emulating the effects of an explosion using radio frequency. And after the concept was developed, prototypes were made, pre-production models were provided. And what we found, comparing it to the initial criteria, there was only one we didn't match. And that was, of course, they're radio waves. They are never going to flow over a building. Okay? So that's a given. The other thing we found was we were able to change the maximum charge weight for the explosives from 100 kilograms to 20 tons, and still remain within the ranges that we were looking at. And the other thing, which came as part of the development, was the ability to model fragmentation. Never been an original concept. It was always thought it was going to be too difficult, but with some very clever minds, we were able to develop the ability to indicate fragment throw as a result of the explosion. So what was the system? What does it look like? Well, it consists of a transmitter, which has a screen and a box. In fact, it's probably easy if I flick up the next slide. It has a transmitter, which is the yellow box. It has a keypad and an external aerial and a screen. And using the keypad and the screen, you can select one of 25 types of explosives, which include military, commercial, and homemade explosives. And you can select a charge weight from between 100 grams to 20 tons. You then have a series of receivers, which can be issued to people and participants placed around the area. And they have a series of LEDs. This one is showing the size of this one and has a series of LEDs. It has a green LED, which shows that it's actually working, a red LED, which indicates blast effectiveness, an orange, blast lethality, an orange LED, which indicates blast injury, and a blue LED, which indicates you've probably been struck by frag. So a kit will come with the the transmitter, a set of 6 receivers, and all the ancillaries. So diagrammatically, it looks like this, that there's the seat of the explosion. If your red light goes on, it means that the person was, or the object that we're testing was within range of the lethal explosive load. The orange LED indicates that the person will have been injured by blast, and the blue LED, which is much further out because fragments will travel much further than blast, indicates that for that given charge weight and type of explosive, it's expected they will have been struck by fragments. So, great kit. To whom is it of value? Well, 3 user groups have been identified. The first one obviously is bomb technicians, POD operators, those sort of people. The people who can go and practice disarming the bombs that the bad guys leave lying around. And the explosive system is configured so that we can wire an external trigger to it in a training IED. And should the IED function because the timer's run down, an anti-disturbance fuse or a booby trap has been triggered, or the render safe procedure did not work as intended, the switch will close and the transmitter will send the signal out to the receivers. The other team, which is number 3 on the list, is search and assault teams. And for that, we can put out a number of transmitters, again, all wired to booby traps, all feeding back to a central control system, and a number of areas where search teams and assault teams have to act. And if one is triggered, anybody within range, their receiver will indicate whether they've been damaged or killed in this case. And should another booby trap even closer or larger, the LEDs on top will change depending on the damage that that LED has now received from another IED. So the search mode gives us the opportunity to lay out a number of transmitters. But the one that's most relevant to us is the blast assessment. This is the one that's designed for security managers, emergency managers, chief wardens, venue facility owners and managers, and the consultants who advise on explosive damage and protective measures, construction, all of those factors. And we'll talk through a scenario on that a bit later on in the presentation. For those that are interested in the technical aspects, all the calculations are based on the Kingerlee and Bullmarsh methodology, which is mostly famously recognised as the basis for CONWEP, which is the old but very well used and heavily validated blast assessment methodology for doing calculations for charge weights over distance and pressures. The red LED, the one that says that the item or the person was within the blast lethality range, is set at 207 kPa. That is the threshold for lung damage. So if the red LED goes on, the receiver is within the range where the person will have received at least lung damage, probably worse. The threshold for the orange LED, which is the blast injury level, is 34 kPa, which is the threshold for ear damage. Beyond that, unlikely to receive physical injury. Closer than that, or anytime the orange LED lights up, the person is going to be injured. And of course, once you cross the 207 kPa boundary, the LED becomes red. The fragmentation injury LED, which is the blue one, is based on a number of generic assumptions and calculations, because to do specific fragmentation calculations requires exact knowledge of the casing, the orientation, a whole lot of factors which are not going to be known or be able to be programmed in. So some generic calculations using open source information on frag throw have been built into the algorithm, but they work back to 79 joule impact. And that is, again, well documented as significant fragmentation impact and damage. So if the blue LED comes on, it means that the person or object has been hit by a significant piece of frag. The fragmentation calculation can be turned off if it's not relevant to that particular scenario. In all cases, the information that the receivers have indicated is sent back to the transmitter, stored for later download and analysis by whoever's running the scenario. Let's have a look at a couple of the screens and talk through a scenario. This is the home screen for the system. And it has the local date time, which is set into the machine. It has which mode we're in, remembering there's the bomb technician mode, the blast assessment mode, the one that's relevant to us, and the high-risk search mode. And then down the bottom, it tells us the amount of explosive we've chosen, and it gives us the distances at which we can expect the LEDs to light up. And the bit in the middle is a big timer. We go to the settings menu, and one of the first things it asks us to do is select the mode. We're not bomb technicians, we're not high-risk search or assault team, so we choose the blast simulation. Next thing we're asked to do is choose an explosives from either the common menu, which doesn't necessarily mean they're common, easily accessible explosives, but they're the sort of things that we might want to use for our analysis. And they include the commercial and the homemade explosives, and also TNT. Now, TNT is difficult to get hold of. The villains are unlikely to use it, but it is the basis against which all other explosives are measured. So that's there. And for this example, we use TNT. We need to pick a quantity. Now, this needs to be relevant to the actual scenario, the setting, the environment. A simple calculation is that a comfortable one-hand carry is 5 kilograms. Carried by the side of the body is 10 kilograms. Two-arm carry is 20 kilograms. Anything bigger than that's on wheels. So let's say comfortable one-hand carry, briefcase, nobody notices you carrying that around, so 5 kilograms. So we choose TNT, we choose 5 kilograms. Because we're using the blast assessment mode, we use the internal timer. We don't need the external switches. You can do that, but in this, the default is to use the internal timer. And that can be set from 0 seconds to 24 hours. And you can use that for your evacuation training, for your search training, for unidentified item response, all of those sort of things. You can set a timer that you need to have made the decision, evacuated people to a safe distance within whatever time frame is selected. Because we're doing this as just a test of the area to see what would happen if 5 kilograms exploded in this particular site, we'll set the timer for 10 seconds. And that takes us back to the front screen where we can see that we've got 10-second time waiting, we've got TNT 5 kilograms, and it's got the distances at which we would expect the red, orange LEDs to light up, and the fact that the fragmentation calculation is on. We push the detonate button, we get a lovely graphic, and in fact on the actual machine, and these are screenshots, that is actually a beautiful graphic of an exploding gas cloud, and then we get the results. We go round to where we put the receivers, we look at the receivers that people are carrying, and we see if any of the LEDs have lit up. And if they have, we know that that person was too close, or that piece of equipment has been badly damaged and or destroyed. We can use this for structural damage. The way we do that is the orange LED, you'll remember, was set for 34 kPa. Now that's peak pressure, peak incident pressure. This is where the blast wave strikes the surface and that initial pressure is 34 kPa. This is hydrodynamics. Workable similarity is a wall of water. Wall of water strikes the surface. If it doesn't immediately fail, it will build up and build up and build up against that surface until either the surface fails or the wave is reflected back. And that's known as the reflected pressure. Based on some assumptions, our peak incident of 34 kPa when the orange light triggers equates in general terms to 70 kPa reflected pressure. And that well and truly exceeds the structural strength of any building materials, with a few exceptions. But generally, for anywhere we're working and playing and living, that means that that local area near the device, wherever the orange LED lights up, has suffered significant structural damage. So how do we use this? For example, we go to a site and we say, where will you let me enter carrying anything I like? This is a public area. I can come in carrying 5 kilograms. Fine. Where can I put that 5 kilograms? I can put it against this wall here, walk out, maybe nobody will notice. So we can place the receivers around to see where would the lethal danger radius be, where would the injury dangerous radius be. But also importantly, we say, what's on the other side of that wall? And the answer is it's the computer center, or it's the boardroom, or it's the kids' crèche, or whatever it might be. Fine, we can suggest graphically now that if 5 kilograms explodes here, that part of the wall will fail. And whatever's on the other side of that wall will be severely damaged. So we actually have a visual, real-time, real-world indication of the results. We can also use it to test our bomb threat responses. As I said, response to unattended items, practice our emergency drills. Oh, it doesn't matter if we go down this staircase, yeah, the bomb's on the other side there, it will be right. Well, let's put some receivers in there and see what happens. Yeah. So we can use it for structural damage as well. The thing that we need to stress is this is an incredible system. It takes radio frequency, which is one form of physics, and using some very clever software algorithms and computing power is able to emulate blast and fragmentation effects for 25 different types of explosives, from charge weights from 100 grams to 20 tons. We've deliberately limited the range of the system to 250 meters. That's more than adequate for most scenarios, and we deliberately don't want this to be too powerful. It uses Wi-Fi. It's safe to use anywhere you can use Wi-Fi. There are some places you can't use Wi-Fi. I would suggest they're the same places you probably can't use pyrotechnic training devices as well. I stress again that we use the word emulate. It indicates the effects. It doesn't create them, but it does it to a very high degree of accuracy. So the clever part is using the RF, deliberately limited to 250 meters. There are variations between RF and blast, and we know those and we accept them. And in fact, what we found was that they actually replicate the Murphy's law of blast. And a simple example is if I'm facing the receiver and I have I'm facing the transmitter and I have my receiver mounted here, then it will receive a full signal. If I've got my back to the transmitter, my body will shield the receiver and I may get a lesser signal. If I am facing an explosion and if my mouth is open, I will suffer significant internal lung damage. If I am facing away from the explosion, I will suffer less damage, again, given distance and a number of variables. If I am laying down on my receiver, I will smother it and receive less signal. If I am laying down when a blast wave rolls over me, I will suffer less damage. So what we found was that the variations we get with RF equate to a reasonable degree to the variations we find with blast. And the reason why on the screen it indicates the distances at which the red and orange LEDs should light up, and the variation with the receivers is the real world environment. You will get reflection off buildings. You will get things that will shield the radio signal that may also shield blast. We emulate, we do not replicate. They are similar but different. So we found that the similarities are greater than the differences, recognizing that they are two very different forms of energy. The detailed structural response, the orange LED may have triggered, and that may say, oh dear, this part of the building will suffer significant damage. One of the things that we'll do is overcome the desire for people to say, oh, there's been an explosion, the entire building will collapse. Well, not necessarily, not unless we've actually taken out a couple of major structural elements, or progressive collapse was not a design requirement, or prevention of progressive collapse was not a design requirement at the time. What the explosive system does is gives us a basis for undertaking the CFD analysis. How will this fail? In what manner will it fail? So in summary, after some 25 years of thought, we now have a system that provides a high degree of accuracy, emulation, not replication. This is not a modeling tool. It is an indication of the effects of different explosives and charge weights over distance that provides a reasonable indication of what would happen if this scenario occurred. Bomb effects, blast is still a specialist subject. What this does is place a tool in the hands of many of the users that will give them a good indication of what might happen and form a basis for some rational planning, and also knowing when to call in the specialist's support. On a personal note, I would like to thank Layer 3 Services for having resurrected the project, having put the resources in, and having taken it from a concept and put it with today's modern technology, and to create a working system that does what we hoped. And also for keeping me involved and helping me support what has been a passion of mine for many, many years. And I think the key message to take away from this is, if you have a good idea, whether it be for a piece of technology or a new process or policy or a better way of writing something up, you'll probably get knocked back a few times. There'll be people who say it can't be done, and it may not be able to be done, but don't let it die. Keep the dream alive, and eventually you'll find that the need is identified. And in our case, the technology has developed to the point where the concept could be made a reality. Thank you. Happy to take any questions.
Okay, if anyone's got any questions, we'll get you to put them in the chat window. It's a great presentation. Maybe here's a curly one to get you started, Don. What testing did they base the human injury levels on? Was it the Bowen curves, which are 50-year-old tests on sheet, and are they still valid?
The answer was we cheated. We let everybody else do the testing. We've got technical references, and again, if you go to the Ferrari paper, which is on the Layer 3 Services website, if you go to the Layer 3, the paper, it's under if you go to explosive products page there, and the paper I think is down the bottom. There it is, the technical paper. You'll see that there's something like 30 or 40 references at the back of that paper, and we just looked at what everybody else was saying were the critical elements, and a lot of it comes out of FEMA, out of the US, which relates to their Department of Defense documentation. But you're right, a lot of it does go back to the 1950s tests on sheep and pigs. But a lot of work has been done since then, and there are now internationally generally agreed standards. Like anything with experts, no two of them will agree. One person will say that it's 3 psi for ear damage. Somebody else will say it's 5. We used the recognized main references and said, pick a number. We chose 5 psi, 34.5 kPa. And I hope that answers the question.
Yeah. Any experience using this in a bomb threat evacuation drill, like for warden teams, or is it a bit over the top?
No, that's exactly what it's designed for. A scenario, we haven't done it yet. We've got a couple of sites lined up. We've got the pre-production models. They are not as finely tuned as the actual production models will be. And guess what? Components are held up overseas due to COVID and shipping container shortages and all that. So we have proven it works. We've proven it works to a high degree of accuracy. I'm not willing to say it works, the LEDs light up within 100, 200 or 300 millimeters of the indicated distances or the calculated distances yet, because the pre-production models we've got are not as finely tuned as the production models will be. But we're still seeing a high degree of accuracy, well under, I would suggest 500 millimeters, but I haven't measured it yet. We're waiting till we get the production models, and we already have a test plan laid out where we will lay these out and we will measure them to within 100 millimeters to see how accurate the receivers are. We know they're accurate enough at the moment. So we haven't actually run these out to experiment with them at sites. We've got a couple of test sites queuing up for this. But the sort of scenarios we see is a bomb threat comes in saying there's been a bomb placed in the loading dock, in the food court, wherever. The emergency control organization run out their in-house search teams, and they find an object they don't like the look of, fine. That results in the chief warden calling an evacuation. And if there was a timeline given in the threat, we match that to the internal timer in the transmitter. Wardens are issued with the receivers. Receivers are placed on critical equipment. So when the thing does trigger, if anybody is too close, that little orange LED is going to light up.
Yeah, okay.
That's exactly what it's designed for.
Good question here is, can you apply the system during the design phase before the building or infrastructure has been built, or is it strictly post-construction use?
No. We can do this at basically any time. If you want to know what will happen if I was to put 20 kilograms of homemade explosive in this location, or if it's commercial explosive, one of the pentalites, which are reasonably easily accessible and made in small kilogram type lots. If I put 20 kilograms of that here, because I'm thinking of putting my computer center there, what will happen? Well, let's put it down, do some measurements. Again, this would probably lead you then to say, oh, I think we have a problem. Now I need to do some serious modeling. And again, there are some very good people around who can do that for you.
Yeah. There's a question here from Gary Gibbs. Sorry if I get this wrong, Gary. That's a key point: open source and generic device.
Yes. Okay. Gary has been involved. I'll dob him in. He's been involved and in fact done a lot of the fragmentation work. I think the points Gary's trying to make, if I hope I'm right, is that all of this is open source information. There's nothing classified in this. Everything that we're using is out there. The thing that is not open source is the incredibly clever algorithms and programming, and that's the in-house part. But all the figures, the fragmentation calculations are all based on SWISDAC papers. Yeah, it's all open source out there.
Okay, awesome. Okay, so if any of our listeners today or anyone listening on the recording wants to get more information, what's the best way they can get in contact with you or get access to the product?
Layer 3 services. Go to it's their product. I am involved, and I've been brought on as a non-executive director for the technical input, for which, as I said, I'm extremely grateful. The 3 services, so that's layer number 3 services, all one word, .net.au, and there are contact details there as well.
Okay.
As I said, the design is effectively finished. The production components are on order for the first view. This was not so much a hard sell as this is how you take a great concept and you bring it to fruition, no matter how long it takes. But obviously there is an intent to sell this, and there is nothing like this in the world. Hopefully people will find it useful, and particularly puts, I think, a practical tool in the hands of security, emergency, venue managers.
Okay, well, I think that's all the questions. So thank you so much, Don. Thanks once again for
Thank you all.
Giving us a presentation on Blast. Thank you to everyone who was able to attend tonight, and anyone who's listening on the recording. Thanks for listening into the ACT chapter. I guess everyone should know that our next event is the Security and Government Expo, which is on the 25th of November. And if you go to our LinkedIn page or our website, you will see the details there, and we'll be streaming some of those sessions live. So you'll be able to hear in, even if you can't make it. Wherever you are, we hope you're safe. And if you can see in the chat window there, there's the links. So I hope you're keeping COVID safe. Thank you everyone for taking your time tonight. And hopefully we'll see you at the next one.